Hi all, today's session is just going to be, well, hopefully quite a short one. It's just about integrating with trigonometry. And now I kind of think, in hindsight, I probably should have made this video before, but that's where we are, and I guess we better learn those trig integrals. There's not much to it, especially considering that I haven't shown you u substitution yet, and I haven't shown you integration by parts yet, so you can't do too much with it, but I'm just going to show you the basics of integrating trig functions. So as you see, we have a table here. Those integrals here would seem probably quite unfamiliar, except for those two here, because they pertain to this kind of cycle of integration and differentiation in of simple wave functions, so sine and cosine. So as you know, if you differentiate sine, you get cosine, and then you get minus sine, then minus cosine, and so forth. So that should be familiar actually, but this here is a bit weird. So the integral of tan of x is actually the natural logarithm of secant of x, which is a bit weird to think about, but I'll make a video on that kind of stuff, proving it. And yeah, it should be quite fun. I personally found it fun. But then you have those integrals here, which are basically just the integrals of the derivatives of a common trig function. So I haven't circled it, but just so that you see, you already know everything here. There's a sense of duality, I have to say, because if you differentiate, if you integrate the minus cosecant squared of x, then you get the cotangent. And then if you take a very similar function, the secant, which is also squared but is reversed, so it's like minus, then you get the tangent, which is the inverse of cotangent. And that just, to me, probably spending too much time thinking about things. But anyway, if you know those, then you're good to go. And if you're going to solve some integrals with, like, I don't know, say the tangent of 2x, then you're gonna have to use the trig identities and other tricks and use substitution. And I'll also make a video on that, like a whole kind of episode just dedicated to solving those integrals. But for now, we're just going to solve this really easy definite integral over here. And as I told you before, there's a constant rule, which means that this will be equivalent to the following expression. By now you should know the trick. We kind of pretend this is an indefinite integral. So if an integral with no bounds of sine of x, according to this table over here, equals minus cosine of x, then what we do is we just essentially work out the this thing over here, same expression, with x being equal to our upper bound, and then minus by what you get for the lower bound, which is a negative number on its own. Okay, so then that'll be the same as minus cosine of x, but x equals to pi, and that minus cosine, or actually, yeah, that should be plus because we have a negative expression here. And if I'm not wrong, that should be the same thing as if we just want to make it neater. And now, in the cosine function, what we notice is that it is a symmetrical function. So that essentially means that that this thing over here should be equal to this thing over here, but I'm not sure if it's going to give me the result I wanted, so I'm just going to show you here. So cosine minus pi minus cosine of pi, and we have 0, just like I said, so 0, and I really don't know how much you can see of this, but what happens is the integral kind of cancels out in a way. So if we look at, kind of have this basic intuition here, it maybe doesn't look too clear here, but I'm going to say that this is the area we are talking about here, and because you have a significant, well, we have half of the area here in this integral being above the x-axis and the other half before, like below, right below, in the negative y-axis. So what it basically means is that you end up, if it's a symmetric function or an even function in a more professional terminology, and if you are evaluating it from the same value, just one of them is positive and one of them is negative, then what you should get is essentially 0, because there's no like net, like total, like a visceral total answer. You have a positive area and a negative area, and together they cancel out. So that's it, and in the next video I'll explore U substitution, which is perhaps not the hardest of integration, but people definitely take time to realize that it's actually pretty easy. And I certainly did, that's what I'm saying. And it can be very difficult when you go into more advanced calculus, in which case you start using U substitution, V substitution, W substitution, and so forth. Now, when you have a lot of composite functions, it definitely gets a bit tedious, but it solves so many integrals, and actually it's probably the most smart thing about calculus. So I'm going to show you how to do it in the next video.